Okay. Right. Let's go ahead and share. Okay, there we go. Okay, so are there any questions before we get started with either the nucleophilic attack or the loss of the leaving group steps? Okay, so we'll move on into proton transfer. So for proton transfer, what you need to have is a lone pair of electrons taking, or I guess we could say removing, a proton. Okay, now they look very much like nucleophilic attacks, but instead of attacking a carbon atom that's positive or partially positive, proton transfers require you to have a proton involved. So this H+, the hydrogen cation, is simply a proton in the nucleus. So a regular hydrogen atom has a proton in the nucleus and an electron. So if that electron is lost to make the hydrogen cation, you just have the nucleus left. That's why I've been calling the hydrogen cation a proton. Okay. So for example, in the first case, again, we're not quite yet to talking about product prediction. But if you have acetone in the presence of the hydronium cation, which is an acid component, then what will happen is the lone pair of electrons on the oxygen will take the hydrogen cation. So in order for it to just take the protons, both of these electrons have to go onto the water, which will make a protonated ketone, and then in this case, just water. Okay, so if you use acetone to attack like anything else, because I think we had an example where we used a ketone to attack the boron in some specific, in a molecule, a boron trihydride. Then when the oxygen goes to the bromide, or the boron, excuse me, that's a nucleophilic attack. This is a proton transfer. Okay, so it's not just what is doing like the origination species, it's what that species is doing on the second molecule. So in this case, it's grabbing just a hydrogen cation. In this case, it's attacking an electron deficient species. So this is nucleophilic attack. This is proton transfer. Now, some textbooks don't really care whether you can distinguish those two, but your textbook does. So you will need to be able to distinguish between those two. Okay, so another example, if we take that same acetone molecule and now we put it in the presence of a base, we can use a lone pair of electrons to grab the hydrogen cation, and then those electrons in the sigma bond will go on to the carbon. Okay, now in this case, what you're going to end up with is an allylic lone pair. So these electrons are allylic to the pi bond. So there are going to be times when you make, this would be considered like a reaction intermediate. It's not the product, but it's something that you make on the way towards forming the product. So when you write down that you have a reaction intermediate, you have to consider whether or not something is going to happen to that intermediate, or if your intermediate is stabilized by resonance. Okay, and in this particular case, this is the better resonance structure, because when you compare the two atoms that are being asked to carry charge, you have an oxygen and a carbon. Well, oxygen is more electronegative than carbon is, so it's going to be easier for the oxygen to carry the extra lone pair than it would be for a carbon atom. So this is actually the more dominant species at equilibrium, but this is the species that you would write as a result of the first step, which is the proton transfer. All right, are there questions about proton transfers before we look at rearrangements?
I have a question.
Karen?
Do proton transfers pretty much always just involve hydrogens?
Yes, they will only ever involve hydrogens, but they can't. You have to be careful because there's three different, you have to be careful when you just say hydrogen. Like if you say the word hydrogen, what that means is this, a diatomic species. The hydrogen atom would be the nucleus with one electron on the, or in the 1s orbital. Okay. You can have a hydrogen anion, that's called a hydride, or a hydrogen cation, which is called the proton. Okay, so this is the species that we're talking about. So just make sure that you don't confuse what is actually happening, because this isn't a hydrogen transfer, it's a proton transfer. So this is a hydrogen atom right now on this molecule because there's two electrons in this bond. One would technically belong to the hydrogen, the other belong to the oxygen. It's just that they're polar towards the oxygen atom. So when the lone pair comes and takes the proton, what it's doing is it's filling this 1s orbital, which is mostly empty because the electron that's supposed to be in it is closer to the oxygen.
Thanks, that helps a lot.
Okay, good. Okay, any other questions before rearrangements? Okay, so when we're talking about a rearrangement, we're only going to be looking at a certain kind of rearrangement. And the rearrangements, well, it's going to be two different rearrangements on the same kind of species. What we're talking about is carbocations. So remember, carbocations are going to be carbon atoms that are making 3 bonds, right? And then they're sp2 hybridized, which makes them trigonal planar. Okay, so this species is like flat on the whiteboard, and then coming up towards the camera would be one lobe of the p orbital, and then below would be the other lobe of the p orbital. This is, carbon has a positive charge. So carbocations, so let me write that real quick. You have one hybridized p atomic orbital. So carbocations, though, are products, or they're intermediates in reactions. So what I mean by that is you would have a reactant, and then it would undergo some reaction, so it doesn't matter what it is right now, and you would make a carbocation. Okay. Now, you have to consider here, will it rearrange to make another carbocation before a reaction takes it to product? Or will it immediately go to product with no rearrangement? So what that means is that not all carbocations are equivalent. Now they're all going to sort of have this same structure around the carbon atom, 3 bonds, an empty p orbital, and a positive charge. But when we say that they're not all equivalent, what we have to do is we have to look at the 3 things bonded to the carbon. Okay. The identity of those things will impact stability. Okay. So I don't really have, I guess I do, I have enough room down here. It's a little low. So the types of carbocations that you can have 3 things bonded to them, 3 hydrogens, excuse me. Then you could have 1 hydrogen, excuse me, 1 R group. Ugh, I haven't had enough coffee today. 2 R groups, 3 R groups. Okay. This one is called a methyl carbocation. This is called a primary carbocation. Primary means that this carbon atom is bonded to 1 other carbon atom. This carbocation here is bonded to 2, so that's secondary. This has 3 R groups, that's tertiary. Stability increases in this direction. Okay, so a tertiary carbocation is more stable than a secondary, which is more stable than a primary, which is more stable than a methyl. And methyl carbocations are so unstable that they don't readily form. So when we're talking about that in terms of will they actually form, so you can say how to tell if something will form. And we'll spend a little bit more time on these energy level diagrams when we review the first part of 6 today. Okay, so if you want to tell how, or look or describe why something will or won't form, what you need to do is look at the relative energies of those species on an energy level diagram. So an energy level diagram has a XY axis. Right. And so this one will be for the methyl, this will be for primary, this one will be for secondary, this one will be for tertiary. Right. So the y-axis will be an energy axis. The x-axis is progress. So we're going in that direction. So what that means in terms of progress is reactants are shown first and then products would be shown later. So we're just going to put the reactant molecules here, and something has to happen to this reactant in order for the methyl carbocation to form. Something would have to happen to this reactant to form the primary carbocation. Okay. If something has low stability, it has high instability, which means it's a high energy species. Okay, so this would represent the methyl carbocation. Primary carbocation, secondary carbocation, tertiary carbocation. So the stability, it means it's a low energy species. Okay. in any case, we're trying to go uphill from low to high. Okay, and so the reactant energy diagram will look like this. There'll be a little hill before you reach your intermediate. Okay. The height of this hill is called the activation energy. Okay. It's the cost associated with forming this species. If the cost is so high or very, very large, the process won't occur. Okay, so this activation energy is so great that this thing doesn't form. Okay. This is a little bit lower activation energy, lower activation energy, lowest activation energy. Okay. So the height of the hill tells you how much energy it's going to cost for a process to take place, but it also tells you how quickly something will take place. So this reaction is likely and relatively quick, okay, because it's a low energy hill. Okay. This is unlikely, and it will be very, very slow, to the point where you could say, well, in the relative scheme of my life and doing this reaction, this will not happen at all. So you can say, I won't form a methyl carbocation. I won't form a primary carbocation, but I can make secondary and tertiary carbocations. Okay. So when you have a reactant that undergoes a process and you make a carbocation, you have to determine whether or not that carbocation, let's say you do something and you make a primary carbocation. That primary carbocation is going to try to rearrange to make itself a more stable carbocation. So you would go from things that are low stability to high stability. You would never take a tertiary carbocation and destabilize it through rearrangement. You're always trying to rearrange to get towards the right-hand side of this stability. Are there questions about that before we look at the two kinds of ways that these carbocations will rearrange? Okay. So the two types of rearrangements we're going to look at. The first one is called the hydride shift. Okay. And again, a hydride is a hydrogen anion. Okay. And if we're going to shift the hydrogen anion or the hydride, it means it's going to move from one carbon to another. But it can only move one carbon over. Okay, so it has to move to a next door carbon. It can't move wherever it wants on the molecule. It's a very small distance that it is allowed to move. Okay. So you can only look at next door neighbors. So let's say we have a reactant that undergoes a process and we make this carbocation. And I'm just going to draw this hydrogen here for clarity. Okay. So this is the original carbocation formed. Okay, now in reality, you can't freeze these, but in your mind, once you draw it, before you say what's going to happen next, you have to determine whether or not this thing will undergo a change within the reaction container. So you would look at this carbocation originally formed and you would say this carbocation is secondary. Okay. There are only two next door neighbors, this one and this one. Okay. There's other carbons. There's a CH3 here and a CH3 here, but they're not next door neighbors. Okay, they're too far away. So it's only these two. And there's hydrogens here. Okay, so if you move and shift down to this position, you would end up forming a primary carbocation. If you move over here, you are going to make 1, 2, 3, a tertiary carbocation. Okay, so you're always going to go from low stability to high stability. So the way that this works is the hydride, the hydrogen with the sigma bond electrons, has to move. Okay, so you can't just take the atom, you have to take the electrons. So you start on your sigma bond and you move over to the carbocation. Then what you make, and that hydrogen now is over here, and the carbocation is here, which is tertiary. And then you would make your product. Okay. Now, this carbon with the secondary carbocation does have a hydrogen on it. So there's going to be 2 over here. Okay, so I'm not violating the octet or anything, but I'm just not drawing the hydrogens I'm not interested in. Second type of rearrangement is called a methyl shift. And that's kind of not the best word for it, because really it's a methide shift, because what you're taking is a CH3, which is a methyl group, but it has to have electrons on it. Okay. Again, your methyl can shift from one carbon to another, but it can only move one carbon over. So now what we'll do is we'll draw a similar carbocation as we'd had before. Okay. And again, we have only 2 next door neighbors. One is here and one is here. Okay. This carbocation carbon is bonded to 2 other carbons, so it's secondary. If we shift, we have hydrogens over here, but the carbocation would end up primary. If the carbocation can be moved over here, it would end up tertiary. Okay, now this carbon, as it's written, is actually quaternary. It has 4 carbons attached to it. Okay, but if we remove one of these methyl groups through a methide shift with these electrons, then we'll make a tertiary carbocation. Okay, so we're going to shift we're going to shift so that we end up with a carbocation in the tertiary position. So the methyl has to move with these electrons. So your arrow has to start on the bond and go to the positive charge. And it would end up here in a tertiary position. Okay. Now, a couple points that we have to make. If you look up here, we had a hydrogen and 2 methyl groups. So why did we move the hydride instead of the methyl? Well, a hydrogen anion is smaller than a methyl group. So it's energetically less stressful to move the hydride. So you're going to move a hydride before a methyl due to energetics. Okay. Now in this case, yes, you have hydrogens down here and methyls up here, but moving a hydride shift from here makes an unstable carbocation, so that won't happen. So you're forced to do the methyl shift over the hydride shift. Here you have a choice. Move something small or move something big. It's always going to be easier to move the smaller item. The second thing to consider is that this process, the methyl shift and the hydride shift, these are going to occur very fast. And that's because they involve only one molecule. Okay, and you can kind of think about that, like if you decide that you're going to go to the beach and you're going to go to the beach alone, it takes you less time to get ready and get there than it does if you're waiting on other people. Okay, so if you have a task to perform and it only requires a single molecule, that will be a faster process than something that requires 2 or 3 molecules. Because if a process involves more than one molecule, you have to wait for those molecules to collide, but they have to collide in the correct orientation and with the correct energy. So not every collision is going to lead to the reaction taking place. But something that involves only one molecule with an intra, so within one intramolecular change, these will happen very fast. All right, are there any questions before I give you a carbocation to rearrange on your own? Okay. So what I want you to do, excuse me, that's not a very pretty molecule, but that's okay. Okay, I want you to identify, like by primary, secondary, tertiary, the original carbocation. And then I want you to identify the best shift. And then I want you to draw the rearranged carbocation. I'll give you a few minutes to do that. Okay, does anybody want or need more time? Okay, so excuse me. So our original carbocation is bonded to 2 other carbons. So our original carbocation is secondary. Okay. The next door neighbors are these 2 carbons with the red sort of now black dot. Okay. On these 2 carbons, we have 2 hydrogens, a methyl, and a hydrogen. Okay. If we use these 2, the carbocation will end up secondary. If we use something over here, the carbocation will end up tertiary. Okay. So the best shift will be to use the carbon to the right. But we have to distinguish between the groups. The easier thing to shift will be the hydride. That'll cost less energy than shifting that methyl. So the hydride will shift to this position. Your resulting carbocation will look like that. Okay, so when you have to decide whether or not a shift will occur, a primary will shift to a secondary. A secondary will shift to a tertiary. Primary will shift to tertiary. But a secondary won't shift to a secondary. So you're not going to move that carbocation and spend the energy doing that unless it results in a carbocation with an increase in stability. Okay. Now what we have to watch out for though is we have to watch for shifts that result in a carbocation that is resonance stabilized. Okay, so we could do a shift secondary to secondary, but the shift would be to an allylic secondary position. And I'll show you what I mean by that before we move on. Are there any questions, though, about this carbocation rearrangement? Okay. All right. So let's say that we have a reaction that results in the formation of this carbocation. Okay. So we have a carbocation originally in a secondary position. And just for clarity, we have to remember then that there's a hydrogen here. Okay. Oh, wait a minute. I'm sorry, there's an atom missing here. There's supposed to be a methyl group here. So it's a tertiary carbocation. Okay. If I do a methyl shift, and a tertiary carbocation is a good place to be because it's pretty stable. And so if I shift this hydride over, I'm going to end up also tertiary. Okay, because it would, if the carbocation is here, 1, 2, 3, tertiary. But if the carbocation is here, it's allylic to these vinylic pi bonded carbon. So a resonance stabilized tertiary is better than just a plain tertiary. So these electrons in the bond with the hydrogen will shift to that carbocation position. It will end up here. And then we have to remember that we'll get a resonance structure like that. Okay. Regardless of what is happening, whether the rearrangement will occur or not, you must always stop and think about your carbocation before you propose a product. Okay, because product prediction is going to start in chapter 7. Okay. Are there any questions about these 4 patterns before? I'm going to pull up some slides from the notes for you to do a couple practice things. Okay, let me close these up for just a second. Okay, so these are the last 3 slides of the posted information. And so the types of things that you're going to see on Monday in terms of the exam, it won't be, if it's product prediction, it would be with the arrows shown. It wouldn't be product prediction with no arrows shown. But it's going to be important that if you're shown a reaction mechanism that shows you your reactant and the steps that occur to make the product, and the reaction arrows are shown, that you can label the reaction step accordingly. So when you see a reaction, I'm just going to take a couple colors to do this. This part in the red box this would be step 1. Okay. This would be the reactant. This would be the condition. And this would be, we're going to put it in quotes, the product. It's only the product of step 1. It's not the product of the reaction. Okay. So you would, if you look inside the red box, you would say, well, what's happening inside the red box? Okay. In the first step that's happening, a lone pair of electrons is going to grab a hydrogen that breaks off from a bromine. So this hydrogen is partially positive due to the polarity of the bond. So that step 1 is a proton transfer. So the arrows involve the reactant of step 1. Okay, step 2 is going to take what had been the product that is now the reactant. So what's now in the green box, blue box, excuse me, this is step 2. Now this part is the reactant of step 2. These are the conditions. This is the product of step 2. Okay. Okay. Now, if you look carefully, this species in the blue box that's considered the product is repeated down here. So it's the reactant in step 3. Okay? And if you look at step 3, the only molecule that is involved is the reactant itself. So that would be the rearrangement. Oops, I need to make my arrow, okay, and then this would be the product of step 3. And then the last thing would be that product of step 3 in a step 4. And now this is the final overall product. Okay. So if you look at what's happening, you have a proton transfer to make this species. Okay. Once this species is formed, water is being broken off. It's leaving. So this is the loss of a leaving group to make a carbocation. The carbocation is secondary. A methyl shift is shown to form a tertiary carbocation. So that's your carbocation rearrangement. In the last step, you have a species with lone pairs and a negative charge attacking a positive charged carbon, nucleophilic attack, and you make your product. Okay, so you would have to be able to list or this word, proton transfer, loss of the leaving group, carbocation rearrangement, nucleophilic attack. Okay. So what I want you to do is I want you to spend a few minutes and I want you to do that skill on maybe 1 or 2 of these reactions. Okay, so again, this is the reactant, the conditions, the arrows to form this. These are the arrows to form the 3rd structure. These are the arrows to form the 4th structure. And you just need to write some little note underneath each step in order to identify the pattern of reactivity being shown. I'll give you a few minutes to do that. Does anybody need more time? All right, doesn't sound like it. Okay, so let me get a text box going. Okay, so step one, if you look at what's happening, there's a lone pair of electrons going to take a hydrogen, but that hydrogen is not taking electrons with it, so it's proton transfer. Let's see. All right, in the second step, we have a lone pair of electrons going towards a carbon that's in a polar bond, so that carbon atom is partially positive. That would be a nucleophilic attack. In the last step, you have a lone pair of electrons going to grab a hydrogen without electrons, so again, a proton transfer. Okay. In the second one, lone pair of electrons grabbing a hydrogen without electrons, proton transfer. Second one, lone pair of electrons coming to attack a partially positive carbon, nucleophilic attack. In the third step, this lone pair of electrons is going down into a pi bond, and this RO part is being released from the molecule, so that is loss of the leaving group. In the last one, lone pairs electrons going to grab a proton, proton transfer. Electrons on a carbanion coming down into a pi bond, kicking off a chloride. So that's a loss of leaving group. Lone pairs of electrons attacking a carbon. It's nucleophilic attack. Lone pairs of electrons grabbing a proton, proton transfer. Are there any questions about either of those three reactions? Okay. All right. The last one I want you to practice is this slide, where you're shown the reactant, the conditions, what you make. So I want you to draw arrows on these two species so that you can make this. This species in the upper right is the same as this cation here. So then this cation here is going to react with water to form this species. So I want you to try to draw the arrows. And on the entire diagram, you only need 3 arrows. Okay, so take a few minutes to do that, and I'm going to go switch out the washer for the dryer. Does anybody need more time on this one? Okay, so I'm gonna have to freehand these arrows, which is gonna be ugly, so bear with me. Okay, so we have to look at what's happening over here. We have to end up with this water molecule, the whole thing, H2O, on the molecule at the carbon that had the positive charge. So let me see, before we do that, we can't start on an atom, we have to start on electrons. So let's see if I can get a couple lone pairs on here. Okay, all right. So you're going to take your lone pair of electrons and attack that carbon. And that will make this. So this is a nucleophilic attack. And if we look down here, what we have to do is we have to take this cation and make a neutral species. And so we have to lose, we have OH here, and we have H2O here, and we have to make H3O plus here. So again, we need lone pairs of electrons on our oxygen. Oops, what did I do? Okay, so we take a lone pair of electrons to go grab a proton. Proton can't take any electrons with it, so they end up on the oxygen atom. Okay, pretend that last thing looks like an arrow. Okay. So any questions with that mechanism and the skill of drawing arrows on or recognizing correct arrows?
I have a quick question.
Sure.
So I get the direction of all the arrows except the barbs from the bond to the O, because I thought when I was doing the acid base stuff for homework last night, I thought that the arrow went the other way for that. Is that true?
No, they always have to start on electrons or a bond. You can't start an arrow on an atom.
Okay, that's really good to know. Thanks.
Yeah. Yeah. So just for, I guess I'm assuming your question is it okay if you draw it like this? No, you can't do that. That's absolutely not going to work.
No, the one that is the O.
This one.
Yeah, that one.
Okay. Yeah, you can't go from the oxygen to grab those electrons. The electrons have to go, the line tail has to be on the electrons pointing to the atom that they'll end up on.
Okay, cool, thanks.
Okay, all right. Any other questions before we go back to the whiteboard and we'll review some thermodynamics and the kinetics stuff? So you're not going to have to do calculations. It's just going to be important that you understand the topic. The kinetics, if you have math associated with kinetics, it would be so straightforward you wouldn't need a calculator. Okay, so I'm trying to think what we have going on here. Let's see where we want to start. Okay, so what we're going to start with is enthalpy. Right. And what enthalpy is, it's a state function. So it's given this symbol H. And what it is the heat associated with a chemical reaction. And the heat is related to, or is a measure of, the energy associated with making and breaking bonds. So when you have a reaction, you can have your reactants going to products where the difference in the enthalpy is a positive number. So what this means is it takes more energy to break the bonds than energy you receive when you make a bond. Okay, so remember, making bonds releases heat. Breaking bonds requires heat. Okay. If you have a change in the enthalpy that's positive, the reaction is called endothermic. So endo means enter or to put in. Thermic means heat. So you have to put in heat for this reaction to proceed. You can have reactants that go to products, and you have your enthalpy change that's negative. Okay. These are called exothermic reactions. So heat exits the system. Okay, so one of the things that you have to, that's important to remember, is that the universe is broken up into two regions. You have the system and you have the surroundings. And the system is the reaction. So you can either say that heat leaves the system, or heat enters the system. So when you report the enthalpy, you're doing so with respect to the chemical reaction. You can draw energy level diagrams for these two reactions. Okay. But now we have to have enthalpy as our y-axis, not just energy. Okay. There is a difference between energy, that's E, and heat, which is H, or enthalpy, which is H. So if there's questions about that, I can address those as well in just a minute. If you have an exothermic reaction, the products have to be lower in enthalpy than the reactants. You're still going to have a hill. It's not going to be like a straight down. It's going to have a little bump, but it'll be down like that. The height, the peak height of the hill is going to be closer to the reactant side. It should actually be drawn more like this. Okay. For an endothermic reaction, your products are going to be higher in enthalpy, and then the peak height of the hill will be closer to the product side. Now the placement of the peak height on an energy level diagram is related to something called the Hammond postulate. And so what a Hammond postulate allows you to do is propose a structure for a transition state. So I'll redraw those in just a minute. What is a transition state? Okay, so when you have a reaction, so this is an exothermic reaction. You have a point up here. Okay, so this point is called a transition state. Okay, it's a high energy position for which you cannot, or at which I should say, at which you cannot isolate and study a structure or a molecule. Okay. As soon as this thing forms, it either goes back down the hill to reactants or forward to products. Okay, so this is a hypothetical structure. So what Hammond's postulate tells you is that the structure of the transition state will be similar to the nearest stable energy structure. So this transition state will look more like the reactants than it does like the products. Okay. And you can propose structures all along this hill. And you can use Hammond's postulate to propose those structures. So as you get closer in energy or in enthalpy to the product, you could draw a proposed transition state structure for what you think might be in your reaction vessel at this point. It's going to look more like the products than this point would, which will look more like the products than this point. Okay. So in an exothermic reaction, the transition state looks more like the reactants. And then in an endothermic reaction, the transition state species looks more like the products. Okay. Are there questions about the enthalpy or the energy level diagram so far, Hammond's postulate, or the difference between energy and enthalpy? Okay. So I think I'm going to give you an example of, let me see here. Yeah. No, we're not going to do the math. I'm going to make a decision. We're not going to do math. Okay. So the other thermodynamic thing that you have to consider is what's called the entropy. Okay. And the entropy is given the symbol S, and it's a measure of disorder. Okay. The second law of thermodynamics tells you that the entropy of the universe increases during a spontaneous, as a result of a spontaneous process. So there's a couple different components to the entropy. The first has to do with states of matter. So if you have, and you consider that to be like a beaker, if you have a solid, then your solid is going to be organized highly organized. So this would have low entropy. Okay. Liquids are formed as a result of adding heat. So heat is thermal energy. So what you're doing is you're adding energy to your molecules and you're letting your molecules move a little bit more freely. When you add heat, you're going to disrupt intermolecular forces. Okay, so molecules and atoms that are in the solid state have very little freedom of motion. Okay, you see very little, oh gosh, what's the word I'm looking for? Diffusion. So this atom here isn't going to move to this position here for like 1,000,000 and some odd years. Okay, so it's a very slow process, but you get more diffusion in liquids. And so liquids are drawn sort of just messy. Sometimes you have things that are very close together. Sometimes you have atoms that are not so close together. But this would be a liquid and it has a little bit higher entropy. And then you add in heat again. And you're going to disrupt all the rest of the intermolecular forces so that when you have your gas sample, your gas sample will have the highest entropy or the most disorder. And that's because your atoms have the greatest freedom of motion. So you have no, or you could say little freedom of motion. So you can never really have no motion, but little motion would be just these atoms vibrating in place. In the liquid state, you have freedom of motion. But that is within your sample volume. In the gas, you have complete freedom of motion. Within your container volume. So sample volume and container volume are two different things. So my container here might be 1 liter, but my sample only 10 milliliters. So my sample volume would be 10 milliliters. And the freedom of motion that those liquid molecules would have would be within that 10 milliliters. But if I'm in a gas in 1 liter, then those gas molecules occupy the entire liter of space. They take up the whatever amount of space that you allow them to have. So anytime you have a chemical reaction that will form a gas from solids or liquids, that will be a process that is spontaneous. So you have let me take that back. The entropy of the universe has to increase during a spontaneous process. So that would be a positive change in entropy for the whole universe. The other part of entropy that you have to consider is that your entropy depends on the number of microstates possible. Okay. So if we consider that we have like a piece of instrumentation that looks like a dumbbell, and we have a stopcock in the middle. Okay. And in the left, we have a red atom and a blue atom. And on the right, we have a vacuum. So there's nothing in there. Okay. When we open the stopcock, we're going to have 4 different microstates possible. Okay. They could stay on the left. Oops. They could both go on the right. One could be on the left and the right, or you could reverse it. So you go from having 1 microstate to having 4 microstates. If the number of microstates increases, the reaction is spontaneous, okay, or the process increases. The more molecules you have, the more microstates you're going to have. So if you're going to calculate, and you wouldn't have to do this, but if you had to calculate the entropy, it's equal to the Boltzmann constant times the natural log of the number of microstates. So that takes you into statistical thermodynamics, which we're going to completely avoid. But you have states of matter, and then you have microstates. Okay. Questions about entropy? Okay. So the second law of thermodynamics tells you the conditions of spontaneity. So the second law tells you that the entropy of the universe increases with any spontaneous process. So that would tell you that the change in entropy of the universe is equal to the change in entropy of the system plus the change in the entropy of the surroundings. Okay. The change in entropy of the system is fairly easy to measure. The change in enthalpy of the surroundings is very difficult to consider because the surroundings are literally every single other entire thing in the whole universe, not just in the whole world, but in the entire universe and all that it contains. So measuring that is crazy hard. And it can't even put my mind around it. So what we do, and we're just going to go straight to that reaction, or sorry, that equation, is that we build a Gibbs free energy equation that determines spontaneity from measurable system considerations. So we don't have to deal with the surroundings anymore. We can just combine the entropy of the system and the enthalpy of the system, and we can get a Gibbs free energy equation that will tell us whether a process is spontaneous or not. Okay. So the Gibbs free energy equation is that the change in the Gibbs free energy, that's G, Gibbs free energy. And free energy is the amount of useful energy you can get from a system. And that is equal to delta H minus T delta S. And this is the temperature in Kelvin. So this is the enthalpy term. This is the entropy term, both of the surroundings. If delta G is less than 0, the reaction is spontaneous and will happen on its own. Okay. If the delta G is positive, the reaction is non-spontaneous and will not happen on its own. Okay. So when you consider these two things, it's like saying you have a ball on a hill. And so those are two hills. So you have a ball at the top and a ball at the bottom. Okay. The ball can roll down or the ball can roll up. Okay. And you know from life experience that a ball will roll down a hill spontaneously. A ball will roll up the hill non-spontaneously, which just means on its own. You can get a ball back to the top of the hill, but you have to do something in order for that to happen. The ball is just going to roll. Okay? So what this means in terms of chemical reactions is that if you say if the process of A going to B is spontaneous, then B going to A is non-spontaneous. Okay. So a reaction can only be spontaneous in one direction. You can have energy, free energy level diagrams, and they look just like energy level diagrams, only you use the word, you have G versus progress. Here, delta G is negative, and that's measured right here. Okay, those are called exogonic reactions. If you have to do work to get them to proceed, they're called endergonic. Again, this would be the height of the hill or the activation energy for the process to occur. Are there questions about that part? There is a, one's done. There is a direct link from the Gibbs free energy to equilibrium. Okay. Delta G is equal to delta G naught. That means the Gibbs free energy measured under standard conditions is equal to minus R times T times the natural log of the equilibrium constant. Okay, now KEQ is an equilibrium constant. It's essentially the generic form of saying Ka. The equilibrium constant for acid dissociation is always called Ka. This is just a generic equilibrium. If delta G naught is negative, the reaction is spontaneous and the equilibrium constant will be greater than 1. Both of these two things tell you product favored. So the reaction will proceed towards the right as written. When your delta G naught is positive, that means your equilibrium constant will be less than 1 and it'll be reactant favored. Okay. If there aren't any questions about this link, then we're going to move on to multi-step energy level diagrams. Right. So the energy level diagrams that I've drawn so far today have been for one-step reactions, but you can have energy level diagrams for multi-step reactions. So this is going to be the Gibbs free energy versus progress, reactants, products. So it doesn't, from here to here, it doesn't matter what happens in the middle. Delta G is the difference in enthalpy, or sorry, the difference in the Gibbs free energy between the reactants and the products. So this is an exogonic reaction. Delta G is negative. Okay, it's independent of the pathway we use to get there. So we're going to say that this goes to here, goes to here, goes to here, and then down. Okay. These positions are called intermediates. Intermediates are actual structures and molecules that can be isolated under certain conditions. They can be isolated, characterized, and studied. These bits at the top of the hills, those are your transition states. These are structures that are proposed by Hammond's postulate. Okay. The number of hills tells you the number of steps. So this here is step 1, step 2, step 3. Each of the steps has its own activation energy. So this is the activation energy for step 1, activation energy for step 2, activation energies for step 3. So of these 3, The third step is the fastest because it has the smallest activation energy hill. So these are activation energies. Now, as long as your axis, your y-axis is Gibbs free energy, these are given symbols delta G, and then you write a double dagger. The higher this is, the slower the reaction. Okay. If it's a small activation energy, the reaction is faster. Okay. The activation energy is the only measure of rate of reaction on an energy level diagram. You don't get any information about the rate by knowing that this reaction is spontaneous. It's only if you know the mechanism and the individual energy requirements can you say anything about the kinetics. Okay. Now let's say we have a two-step reaction. Gosh, I'm going through black pens like crazy. We have a two-step reaction. Right, so we have transition state 1, transition state 2, and 1 intermediate. The activation energies are here and here. Okay. Step 1 is the slow step. Step 2 is the fast step. The slowest step will have the highest activation energy. And it is called the rate determining step. The reaction can't proceed any faster than the slowest step possible. Okay. The rate determining step is involved in the kinetics of the reaction. The last little bit of energy level diagrams I want to cover before we talk a little bit about kinetics is what happens when you have a catalyst. Okay. So a slow uncatalyzed reaction you can speed these up. Using a suitable catalyst. And the catalyst provides an alternative low energy route or low energy pathway. So that would be this squiggly line at the bottom. Okay. The activation energy goes from here to here. So it's a faster reaction. Are there questions at all about any of the thermodynamics review before we do a little kinetics review? Okay. So when you look at kinetics, kinetics is the rate of the reaction. Okay, it tells you how fast a reaction is or how slow a reaction is, but it doesn't tell you anything about spontaneity. Okay, so you get no information on spontaneous or non-spontaneous, all you get is speed. And the way to think about this is to think about two different reactions. You can have a TNT explosion, or you can have an iron nail rusting. Okay. Both of these are spontaneous. This takes on the order of seconds. This takes on the order of years. Okay. Diamonds turning to coal. Thank God for men who propose with diamonds. That takes millions of years. They're all spontaneous, but they have different kinetics. Okay. So kinetics is given by what are called rate laws. Rate laws are built from the slowest step in the reaction, which is called the rate determining step. Okay. And rate laws are built by saying the rate, and the rate is measured as the change in the concentration over the change in time, is equal to a script K, which is called the rate constant, times the concentration of species raised to some order. All the orders are experimentally determined. What we're going to see, let me write in one other thing. So these concentrations, this is moles per liter of reactants, never products, but only the reactants that participate in the slow step. So we're going to need to distinguish two different kinds of rate laws. So we're going to need first order rate laws and second order rate laws, which means we have to have an exponent of 1, an exponent of 2, or 2 exponents that add up to 2. So first order rate laws will look like rate equals Ka, and if you don't write a superscript, it's a 1. Second order reactions are either rate equals Ka raised to the second power, or rate equals Ka times B. Okay. You mostly saw rate equals Ka or rate equals Ka squared in general chemistry. In organic chemistry, we're going to use rate equals Ka and rate equals Ka times B. Okay. Right. Now the rate constant, like I said, is you would determine that experimentally, but this is dependent on the activation energy. And the temperature, and something that's called an orientation factor. The orientation factor has to do with what happens when molecules collide, because if they're not oriented in the right way or colliding with the correct amount of energy, the reaction won't take place. So, didn't think about one more thing here. Just looking through the book, making sure I don't have anything missing. Okay. But I'm going to show you how to determine with data whether you would have a first order reaction or a second order reaction. Are there any questions about this general kinetics review? All of my kinetics notes from 102 are posted on Canvas, and they're in chapter 14. Okay. All right, so how you would determine whether something is first order or second order is you would have to have, it's called the method of initial rates. It's going to take me about 5 minutes to go through this, maybe 10, but I'll try to be fast. Okay, so we're going to do a couple of experiments, 1, 2, and 3, and our reaction is going to be A plus B goes to C. A, B, rate. Okay. So what we do is we say we're going to do an experiment with some amount of A and some amount of B. And these could be mole values. It doesn't really matter. Okay. And we're going to say that the rate, I'm going to use really simple numbers just so we can do the math in our head, is 2. Okay. Then in the second experiment, I'm going to increase the amount of A, but I'm going to leave B alone. Okay. And oops, see what happens to the rate. Then I'm going to do a third experiment in which I keep A the same, 1 to 1, but then I change B, 1 to 2. Okay, so I have these 3 sets of experimental data. And then I compare 2 experiments at a time. So I'm going to compare experiment 1 to experiment 2. When the concentration of A goes up by 2, the rate of the reaction goes up by 2. So I would say 2 to what order, I'm going to use an N, equals 2. So N would be equal to 1, and the reaction is first order with respect to A. Then I do the same thing, but I pick experiments that I can measure the impact of the change in B. I go from experiment 1 to 3. B goes up by 2, but the rate is unchanged. So then for B, you would say 2 to what power is equal to 1. So M would be equal to 0, which means B is not involved in the slow step. So my rate law would be rate is equal to some rate constant times the concentration of A. So this would be a first order reaction. If doubling B had doubled the rate, then it would have been a second order reaction. So that's about as much of a review as I, well, technically have time for and really think that you need. Can you guys go down to the participants thing and tell me if you felt like that was worthwhile, worth the time to go through that? Feel a little bit better about that? Okay. I'll make sure that I talk to Dr. Barrios Sosa about it, but I'm pretty sure that my assignment of writing the exam includes this first part of 6, so I can write the questions however I want, and I'll do it based on how I taught you the material. So there you go. Okay. All right, so are there any questions before we end for today? Okay, so this is the end of the material that'll be tested on Monday. So tomorrow we're going to start chapter 7, and if you have not been printing out the notes, I think it's going to start to be helpful if you do, because you'll need a lot of things kind of drawn in order to make the reactants or the reaction mechanisms go a little bit faster. And then we'll talk about organizing the material and moving on with it after the exam, but we'll start 7 tomorrow. All right, well, if there aren't any other questions, I will see you guys tomorrow, and I will put the Zoom notes up as soon as I get them. Yesterday, they were really, really slow in getting to me. All right, I will see you guys later. Have a good day.
Thank you very much.
You're welcome.